Hi, Chris Good here, and we're going to do the solution to the independent groups ANOVA practice problem 1, which I've opened here. This is posted on the, and thanks to Linda Wolf at Webster University for providing this sample problem. This is on our iCollege website. So, a research study is conducted to examine the clinical efficacy of a new antidepressant. Depressed patients were randomly assigned to one of three groups: placebo, low dose, and moderate dose. After 4 weeks, patients complete Beck Depression Inventory. This independent groups designed 3 different groups of different patients. The higher score, the more depressed the patient. The data are presented below. Compute the appropriate test. So the appropriate test here is analysis of variance, and we're going to do that here. Here are the data. We know now that to get an answer, we're actually asking a question about the means. So we're going to look at the means within this group and just copy and paste to get means for the other groups. Right? We're going to bold these, move some stuff around, do our alignment and things like that. In an early example, I did the grand mean to compute sum of squares total. I'm not going to do that this time. I'm going to do it without doing sum of squares total. I'm actually going to do deviations within each group to get the sum of squares within treatments. So actually really interested in sum of squares between treatments, and we're going to do that second. The first thing we're going to do is we're going to do all the steps of the null hypothesis significance test. So step 1 is to state the null hypothesis, and for ANOVA it's that mu1 equals mu2 equals mu3. Nothing equals 0. It's that all 3 population means that these samples came from were the same, or at least had the same mean. We can look up F-crit, but in order to do that we're going to need our degrees of freedom in the numerator and degrees of freedom in the denominator. Let's go ahead and do our degrees of freedom between treatments. That's going to be equal to k minus 1. So we should put what k is, I suppose. K is, well, we could do it this way. We could just count the number of groups that we have. Well, it can't, no, it won't count text. Well, let's just say 3. Alright, so we have k equals 3 groups, and degrees of freedom between treatments is just k minus 1. Degrees of freedom within treatments, that's going to be our denominator degrees of freedom, is equal to big N minus k. Alright, it's returning -3 because we haven't counted our n yet, but we can do that by counting how many scores we have, right? And then, so once again, we're looking at 2 degrees of freedom in the numerator, 12 degrees of freedom in the denominator. Here's how to use the table, the F table. There's 2 in the numerator, 12 in the denominator. For an alpha of 0.05, that's the light phase type, is 3.88. If we had used alpha of 0.01, we would have used 6.93. But we're going to use alpha of 0.05. F crit for 2 and 12 degrees of freedom is 3.88. Okay, we can do step 3 is to calculate F. In order to do that, we need sum of squares between treatments and sum of squares within treatments. Sum of squares between treatments is the sum of t squared over n minus g squared over big N. The t squares, that's t is the total of each within a group, and n is the number within a single group. We're going to square those totals, divide by n, and then g is the grand total. That's the sum of all of the scores, and we're going to square that and divide it by n to get the second part of our sum of squares between treatments. T's are pretty easy. They're just the sum within a group, right? And then we could do t squared down here. That's just our t's squared. Don't worry if you get big numbers here. You're squaring stuff. You're going to get big numbers. We can divide those by n, little n in each group. This divided by know it says divide by 0. That's because I haven't calculated n yet. But if I just count how many squares are in my group, right, it's going to fill that in automatically. Okay, so we've got the first part of sum of squares between treatments. We've got t squares over n's. We just need to sum them up. But I need g squared over big N. I could put g squared over here. We've got room. That's g squared. I think I can go ahead and do it now. So we can solve for sum of squares between treatments by taking the sum of t squared over n, these, and then subtracting this quantity, g squared divided by big N. Alright, so that's our sum of squares between treatments. Sum of squares within treatments is just going to be the sum of all these sum of squares for each treatment. I know it says 0 right now because we haven't filled anything in yet, but that's what it is the sum of all of these things. How do we get sum of squares here? Well, we're going to need to calculate deviations for the placebo, low dose, and moderate dose groups, and then we're going to do deviations squared. So these are just subtract the mean for that group and making sure to reference that mean all the way down in this column. And we're going to do, with the low dose, subtract the mean for that group, right? And reference that mean all the way down. Lastly, for the moderate dose group, it's the moderate dose minus the moderate dose mean, and reference that same mean all the way down. Alright, and then we're going to square those deviations. So for the placebo group, square that. This is the squares for all the placebo group. Oops. Come on. Placebo squared. And that's the low dose squared. So if we just copy and paste these, they will update with their relative cell references all the way across. Okay. We're going to sum within this group the squared deviations. Do not sum the deviations, sum the squared deviations. That's what SS is for. So you can just copy and paste those, and this sums the placebo squared deviations, this sums the low dose ones, and this one will sum the moderate dose ones. And so now to get sum of squares within treatments, it's already calculated because that references these three cells. Okay, there we go. Now all we need to do is get the mean squared between treatments and the mean squared within treatments. Mean squared is variance, so it's sum of squares divided by degrees of freedom. It's sum of squares divided by degrees of freedom. So now we've got 756.2 over 67, and F is just mean squared between divided by mean squared within. Oops. Let's fix that. F is mean squared between over mean squared within. F is pretty big. It's over 10, and that's okay. Let's take a look at our F table. Oh no, we already got our F crit, didn't we? It's 3.88 because we had 2 and 12 degrees of freedom at 0.05. So 3.88. If 3.88 is here, then 2140, clearly in this shaded region to the right, positive there. And so now we reject the null hypothesis, right? A significant difference exists among these three means, with F of 2 and 12 degrees of freedom equal to 11.21, and P is less than 0.05. Now, we're not done, because since we found a significant difference, we need to find out which one of these means is significantly different from which other ones. And in order to do that, we're going to calculate something called Tukey's HSD. All right, and Tukey's HSD is Q times the square root of MS within treatments divided by N. What is Q? Well, Q can be found on the Q table, and it's the next table here. The studentized range statistic, that's what Q is, and you look it up by looking up K, the number of treatments, and then degree of freedom for the error term. The error term is the denominator. The denominator here is within treatments mean squared, so you use the within treatments mean, within treatments degrees of freedom. So if K was 3 treatments and we had 12 degrees of freedom in the error term, Q at 0.05 would be 3.77. Let's write that down. Our Q is going to be 3.77. And what the honestly significant difference tells you is how big does a difference between two means have to be in order to be significant. So the difference between these two means, right, is this minus this. 17.8 is the difference between the placebo and the low-dose mean. Is it significant? I don't know. We need to calculate the honestly significant difference. And if that difference of 17.8 is bigger than the honestly significant difference, well then it's significantly different. Okay, so let's follow the formula. What is it? It's Q times the square root of the quantity MS within treatments divided by N. Now this only works when you have the same number of participants in each group. But here we go. HSD is equal to Q times the square root, that asterisk is how you do times, the square root of MS within treatments divided by N for a single group, which was 5. There it is. So this is how big a difference has to be in order for the difference to be significant. Let's see what the differences are. Let's do placebo minus low dose, placebo minus moderate dose, and low dose minus moderate dose, and see what differences these are. So placebo mean minus the low dose mean. Okay, placebo mean minus the moderate dose mean. Okay, the low dose mean minus the moderate dose mean. Okay, so these are our differences that we've found. Whoopsies. These are the differences that we found, and they need to be bigger than this in order to be significant at the 0.05 level. So this one is significant, this one is significant, this one is not significant. And we can amend our sentence and say, patients taking the low and high doses, I'm not going to capitalize those, there's no need to, doses scored, no, not low and high, it's low and moderate. Patients taking the low and moderate doses of the antidepressant scored significantly lower on a measure of depression than did those taking the placebo. HSD is equal to 13.845. Later we'll find out how to say exactly what the means were in APA style, but for now I think that this is sufficient, provided we can add our alpha that we used to look up Q in the Q table. And that is the end of the problem.